from Seoul-Tokyo. Despite its diffuse interface model for non-Newtonian two-phase flows with vector density.
Thank you for your introduction. First of all, I would like to thank the organizers for giving me this chance to talk in here. So, the title of the talk is on a diffuse interface model for non-Newtonian two-phase flows with much densities. And this is a joint work with Helmut Abels from Regensburg in Germany and Lars Diening from Munich. So let's start. We consider a diffuse interface model for two-phase flow. The equation is something like a couple system, and the Navier-Stokes type equation coupled with Kahn-Hilliard equation. And here, this is Navier-Stokes equation, and here rho is density and b is velocity of the fluid, and S is stress tensor, which depends on C and dV. C is concentration of the fluid. And we consider two-phase, so this is regarded as concentration of one fluid or the difference between the concentration of the two fluid. And dV is the symmetric gradient of the velocity, and the P is pressure here. And the delta and the M are constant. And okay, so this can be regarded as some exterior stress tensor corresponding to surface tension, and we assume a divergence-free condition. And here M is constant, and mu is so this form. So the and here there is phi is so function, and here there is Laplacian. So Laplacian mu becomes fourth order derivative, and this is the property. So this is Kahn-Hilliard equation. And if m is equal to 0, C flows with the velocity v. But because m is not 0, m is positive, there is a diffusive effect. So this is the main property of diffuse interface model. And because of this diffusive effect, one can easily prove global existence and without confronting the difficulty of the possible singularity of the boundary. So this is the equation, and we describe later the property of phi here. And another property is important point here is the function S, and sometimes this can be, if one considers this term to be equal to Laplacian v, and then this becomes usual Navier-Stokes equation, but this term is not only dV but function of dV. This is the property of non-Newtonian fluid. Okay. And we add the boundary condition on the boundary, so Dirichlet boundary condition. And also we put Neumann boundary condition for C and mu. Mu is function of C. So this. And we put initial data as B0 and C0. So this is the equation we consider. And basic assumption of phi, small phi and S is as follows. And small phi is defined by large phi, and omega is a domain in RD. D is 2 or 3, be a bounded domain with C2 boundary, and let large phi is in this class, so continuous function in the closed interval A and B, and C2 function in open interval A and B. And small phi is the derivative of large phi, and small phi satisfies if limit goes to if phi goes to A, it tends to minus infinity, I think. So this is okay. So minus infinity, and small phi is, if S goes to B, it is plus infinity, and phi prime is larger than minus alpha for some real number alpha. And so M is positive number, as I said, and S is this function defined here and taking value R D times D. So that so here absolute value means Hilbert-Schmidt norm, and if one consider Hilbert-Schmidt norm of SCM, then this can be estimated by symmetric part of M, Hilbert-Schmidt norm of symmetric part of M to the power of Q minus 1 plus 1 times constant. And if one consider difference, we have this kind of estimate concerning Lipschitz with respect to C, and also we have some growth condition concerning M part. And the third property is if one consider inner product, which means one take inner product component wise, so it just as usual as vector. Since we consider matrix, we use the notation, this notation, and this is bounded from below, but so symmetric part of M to the power of Q, and K is constant, positive constant, and there is some also positive constant C1. And C and C1, C2, of course, that moves within the interval A and B. And the Q here is in this interval 6/5 and infinity. And moreover, we assume for every C, this function is strictly monotone. And what is strictly monotone is so this condition. So for any symmetric matrix, D times D matrix, we have this if M1, M2 is different. And we, for the following, we denote E mix C. So this quantity, so nabla C, absolute value of nabla C to the power of 2/2 integral of this, and the large psi c integral of this. So this sum we denote by E mix c. And Vp is so LP sigma, subspace of LP sigma, which has one derivative in LP and also vanishes on the boundary. And L2 0 is f in L2, and which has integral 0, and H1 0 omega, so and there is parent height, and is H1 omega intersected with L2 0 omega, and H0 minus 1 omega is equal to H0 1 omega, dual of H0 1 omega. And the Qt is omega times 0t, and the Q is omega times 0 infinity. Okay. So we recall some results on the Cahn-Hilliard equation with convection term. So basic point is this is convection term, and V is given function, and given vector in the domain omega times 0 infinity, and we like to consider this equation and consider the solvability of the equation. And here C0, E mix C0 is finite, and the V is in this class, and the phi and the psi, phi is derivative of psi, and psi is as in basic assumption. Okay. So this is the result concerning the solvability of the previous equations. So this is the result by Abels and Wilke. So let V is in this class, and then for every C0 in H01 omega with E mix C0 is finite, then there exists a unique solution C in this class. This is bounded continuous function with values H10 omega of the previous equation with which satisfies derivative of C with respect to time belongs to here, and the mu belongs to here. And this solution satisfies this equality for all t, and which satisfy this estimate. So this is basic energy inequality, and this can be obtained by multiplying some suitable function to the equation. And here, H1 is standard H1, and here there is notion of L2 U local, and this is the L2 local function, which L2 norm in each interval with length 1 is bounded uniformly. And here R here is 6 if t equals 3, and if R is in this range if t equal to 2. So this result can be proven by using maximum monotone method, and since there is some perturbation term here, one should consider suitable perturbation theory of maximum monotone operator. And this is done by Abels and Wilke. Moreover, there is this property of the solution. We fix R positive, and then solution C in this class depends continuously on C0V. V is given and the C0 is initial data in this class with this condition with respect to the weak topology on Y and the strong topology on X. So if so this converges strongly, we consider the sequence in this set, and if this converges strongly on X, then the solution C converges weakly on Y. So we consider weak topology by just consider if one, it's clear if one considers 0 T finite. Okay. And for the definition of approximate system, to solve the original equation, we'd like to solve the first approximate system. And one point is that here there is some cutoff term, and here there is some regularization term. And this basically cuts off the large value. If V takes large value, then this becomes 0. And when epsilon goes to 0, 1, so this is some kind of cut function which converges to 1 when epsilon goes to 0. And this is the regularization term which is defined by this, and phi is a symmetric kernel, and with symmetric kernel with this condition, and phi epsilon x is this scaling of phi, and one consider the convolution of W with phi epsilon and restrict to omega. So to consider convolution, W is extended by 0 outside of omega, and then restrict to omega, then one take Helmholtz projection, which projects vector fields to divergence-free vector field, and which is bounded in LP. So we consider this regularization kernel, and another here we also add the regularization term. Then this can be solved relatively easily. So this is our result, and for given T finite and D0 L2 sigma, which is so divergence-free L2 vector field in omega, and C0 in H1 omega, so that C0x is A and in this interval almost everywhere in omega. Then there is this weak solution of dc mu of the approximate system such that this satisfied. And one characteristic of the non-Newtonian fluid or power law fluid is this is not standard energy class, but one here LP enters, so LP. So and C is in this class, and mu is in this class, and R is 6 if D is equal to 3, and R is arbitrary if D equals 2. And moreover, for each time T, there is this energy equality holds. And also for C, this inequality holds and the CTE0 depending continuously on T and E0. Okay, so way to solve this equation is so first B is given and then solve C. So solve this equation using previous results, and then plugging in this solution to this equation, and then so one consider suitable mapping, and then one can use fixed point argument combined with so using Luray-Schauder theory. And we didn't give a definition of weak solution of approximate system, but we give a definition of weak solution for original system. So that is similar. So we give it for original system. And let D equal 2 or 3, and let omega be a bounded open set with C2 boundary, and the T is finite. The phi and the S satisfy the basic assumption. And let D0, C0 in this class such that this holds. Then a triplet such that this class exists where exists is missing, where R is satisfy this condition as before. And this class function in this class is called a weak solution if this satisfies. So this is one takes C infinity function in Qt, which is divergence free, and this divergence of course with respect to space, and support omega is in omega times 0t. So please notice that this is somehow C0 infinity function here, but the support exists at 0 also, so it doesn't vanish on 0. So, and one can obtain this formally multiplying the phi to the equation using integration by parts, one obtain this. And the phi is also, if one consider the C0 infinity function but with Fahrenheit, which means which doesn't vanish on the boundary 0 and omega bar. And if one multiply that equation and taking integral, we obtain this. And one take in this formulation, one can take into account Neumann condition of C and mu. Neumann condition of mu. And we also assume Neumann derivative of C is at the boundary is equal to 0. So this is our main theorem. Let D equal 2 and 3. And let omega be a bounded open set with C2 boundary. And assume phi and S satisfy the basic assumption. And let D0, C0 and satisfy this. Then there exists a weak solution of the original system. So I'd like to first of all sketch very brief sketch of a proof. So there is a unique weak solution of the approximate system together with boundary condition from previous theorem 2. And we passed the solution to the limit when epsilon tends to 0 using an adaptation of the Lipschitz truncation method, which was used for the construction of weak solutions of the power law fluid equation with the low powers in Dunium, Ruzicka, and Wolf. And then we get a weak solution of original system. So main difficulty is the use of Lipschitz truncation method. And I'd like to state of the art of power law fluid equation. So to know the usefulness of Lipschitz truncation method, which is used for the construction of weak solution of this equation. So this is power law fluid equation, and S is a function here, and satisfy this assumption as before, but there is no C, of course, and S is strictly monotone. Okay, so and yeah, of course, S is identity case is easiest, and this is usual Navier-Stokes equation, and this becomes Laplacian. But this identity case corresponds to Q equal to 2, as one can easily see. And basically, this equation is easier when Q is larger, and when Q is smaller, it's the existence of the solution becomes more difficult. And so typical function which satisfies this is just Hilbert-Schmidt norm of, so the Hilbert-Schmidt norm of m to the power q minus 1 plus 1, something like that function is typical function. And we reviewed the known results about weak solution of power law fluid equation. And the first result, one of the first results is due to Lajizenskaya and Lyons, Jacques-Lyons. And they proved the existence of a unique weak solution when Q is larger than or equal to D plus 2 over 2. D is, of course, dimension of the dimension, space dimension. And in periodic boundary condition case, that is, if one considers the equation in the torus, since there is no boundary and the periodic, so torus is compact, it is most easiest case. And in that case, Nature's Malek and Ruzicka proved the existence of a weak solution when Q is in this range. But even this case is not so easy, since there is almost 25 years passed from the first results. And the basic method is for Navier-Stokes case, just testing with equation with V and obtaining energy inequality is enough for the construction of the weak solution. But in this case, because of nonlinearity in the stress tensor S, one should also test Laplacian V to the equation. But this testing with Laplacian V doesn't work in Dirichlet boundary condition case, since Laplacian V does not vanish at the boundary. So one can't use integration by parts. But in that case also Nechas-Malek and Ruzhitska first proved the existence of a weak solution when Q is in this range and when D equal to 3. And later, in Dirichlet boundary condition case, Wolf proved the existence of a weak solution when Q is larger than this. And this is, of course, better than this since D plus 1 over D plus 2 is less than 1. And using L infinity test functions and the local pressure method. So what is L infinity test function method is, so since test function B is not L infinity, but so solution is not L infinity, but one can truncate the solution suitably, especially, precisely speaking, truncate the solution of the approximate equation suitably, and then one obtain the existence of a weak solution. The local pressure method is the method which decomposes the pressure and suitably. And maybe I don't have time to explain more, but let's go on. And in Dirichlet boundary condition case, Diening, Ruzhitska, and Wolf in 2010 proved the existence of a weak solution when Q is larger than this using Lipschitz truncation method and the local pressure method. So difference between Wolf 2007 result and 2010, these people's result is using Lipschitz truncation method instead of L infinity truncation method. So previously one truncate test function solution truncate the solution to L infinity function, but of course Lipschitz function is better than L infinity function, and using this truncation one can get better result. And when Q is equal to 2, basically, so Navier-Stokes equation case, and especially Laplacian V case, the existence of a weak solution can be proven in all dimensions more easily. And this is classical result of Jacques Lyons and many other people. And I should review some known results on Navier-Stokes-Cahn-Hilliard equation, and this is due to we don't here Professor Abels don't consider power law fluid equation, but classical Navier-Stokes equation coupled with the Cahn-Hilliard equation, and show the existence of the solution using similar technique using Luray-Schauder theory and the maximum monotone operator theory. And the results on power law fluid equation coupled with the Cahn-Hilliard equation is due to several people. One result is Kim, Cosgliari, Rodriguez in 2007, which showed the existence of a solution when Q is large exponent, sufficiently large exponent, and they also showed uniqueness. And Grasselli-Prazak in 2011 studied the asymptotic behavior of this equation. And our main result treats the case with low Q, which was not treated in the literature, which corresponds to the result in Diening, Ruzhitska, and Wolf. Okay, so but Lipschitz truncation lemma is a bit difficult to explain, but I would like to explain it. U is in this class, so this is basically the class of the solution of the approximate equation, and H, this is matrix in this class. Besides that, this satisfied for all C0 infinity G times 0t. So G is open set in RD. And define using maximum operator in time and space in this set and this set. So basically, if maximal function of nabla u, absolute value of nabla u and h is large, it is a bad set. These are bad set, and we cut off this bad set. So we take any open set including this bad set and cut out this bad part, and then modify the value, and then other part is the same value as u. Then we can, using Whitney decomposition, one can define some suitable cutoff function. Ellipsis truncation one can make. And the ellipsis truncation satisfies many properties. I can't explain because of time. But so especially ellipsis truncation. So here, so this means E is bad part, and except E, it stays with U. And alpha is also, some difficulty arises. One has to consider alpha, distance d alpha, which depends on alpha. Alpha is a positive number. And one should consider sequence of alpha and should change the metric suitably. And this is corresponds to integration by parts formula. Okay. And so basically, by using ellipsis truncation method, what one can show is the following. So one can show that this and by using a priori estimates given in the theorem 2, one can extract convergent subsequence of this convergent subsequence of these functions. But this limit, weak limit, is basically not related except this case. But this and this and the dv, how is the relation, one doesn't know. But and also one should also consider the convergence of C. It is obtained by convergence of nabla C epsilon I. And but to show that the S tilde is equal to SC dV, and the A tilde is V times V, V tensor V is the aim of the ellipsis truncation method, and this part is the most difficult, and one needs ellipsis truncation method. So okay, so but these are very technical, so I can't explain. And this is local pressure decomposition, but I can't explain. So one decomposes pressure in 3 parts, and each part corresponds to this and this and this, and but I can't explain that. I don't have the time to explain these, so I'd like to finish the talk here. So thank you for your kind attention.